Let's take a BuzzFeed quiz. Are you ready? Let's go. I'm going to draw two squares on the screen. The first one I'm going to call A. The key feature of A is that the points on the boundary that I've highlighted right here are included in the set. Now I'm going to take that same boundary and cut it out of the middle of A. We're going to call the new set B. To highlight the fact that the boundary is not included, I'm going to draw these dotted lines and open circles around the edges of B. Therefore, the only difference between A and B is this boundary set right here. If you're into some mathematical lingo, you'll know that A is called a closed square and B is called an open square. Getting right to the titular question of this video, which of these do you think is larger? Do you think A is larger? Do you maybe think B is larger? Or do you think they're the same size? Okay, well we have one of these we can eliminate right away. If you said B is larger, you might want to go back to the start of the video to see if you understand exactly what I'm saying. Either that, or you might be on a higher mathematical playing field than I am. Maybe you're thinking about compactness or some other deep mathematical concept, but that's not what we're going for here. We're keeping it simple. So we'll just eliminate this choice that B is larger. Half of you are looking at the choice that A is larger and asking that I please eliminate it. The other half of you think it's just as obvious that I should eliminate they're the same size, and think it's very clear that A is larger than B. Turns out, the answer to which is larger is way more nuanced than I ever would have predicted. If you said A is larger, congratulations, you're a topologist. And just as nicely, if you said they're the same size, then you, my friend, are a measure theorist. In the next section, I'm going to show you why this question is so nuanced. We'll go over both sides of the argument, and hopefully you'll come out understanding both of them. In the end, we'll see how to resolve this tension by inventing some new mathematics. In this section, we're going to find out why A is larger. Point set topologists, who from now on I'm just going to call topologists, always think of everything in terms of sets. Here I put a couple of examples of two sets on the screen here. The first one contains the numbers 1, 4, and 6. The second one, S2, contains the numbers 3, 6, and 9. Notice that they can contain some of the same elements, but not all of the same elements. We can make sets larger by adding elements to them, like how in S3 I've added 10 and pi, or we can remove elements from sets, making them smaller. Since S4 just contains the elements 9 and 10, we say that S4 is a subset of S3, because every element of S4 is also an element of S3. Often, topologists use these three symbols to represent it. They mean subset or equal, subset not equal, and just subset. This final one is a little bit ambiguous, so we're just going to focus on these two symbols here. A wonderful example of this is the sets that we just went over. Because A contains every point of B and also some more points on the boundary, we say that A contains B, or, in other words, B is a subset of A. You'll notice that the symbol is written in the reverse direction to indicate that A is the larger set in this case. Because A contains some points that B does not have in it, we say that A properly contains B, and we can write this subset not equal to symbol. In topology, every single point matters, and since A contains more points, that means that therefore A is larger. End of proof. This is true for a topologist, but not necessarily for a measure theorist. In the next section, let's see how a measure theorist thinks differently about the exact same situation. If you think like a measure theorist, you like to put numerical values to everything. So let's do that. In this example, we'll say that A's side length is 3 meters. And since you passed middle school geometry, you know that length times height is the formula for area of a rectangle. So the area of this square is 3 times 3, which is 9 square meters. As this animation shows, this calculation is the exact same when we pull out the center and calculate the area of the set B. It's also 9 square meters. They have the same area. We can see this even more clearly if we try to calculate the area of the missing boundary. Let's unwrap it and see what it looks like. Now that the line has been straightened out, let's just remove its hinges. The key thing to remember here is that the thickness of this line is completely arbitrary. In reality, the line is infinitely thin, so I can draw it very thick, or I can draw it very thin. In reality, if I drew it with its perfect thinness, you wouldn't be able to see it at all, so you'll forgive me for making a little bit of extra thickness just so that you can barely see it. Let's draw a bounding rectangle around this. This rectangle includes, of course, every point of the line inside of its interior. We'll keep track of its width, its height, and its area. Now let's shrink it down. As I continue to shrink it, you can see that the area is shrinking along with the width and the height. I'll remove these 2 points here because they are only individual points, and in reality, individual points take up very little, infinitely small amount of space. You can see here that the upper set is a subset, a proper subset in fact, of the lower set. Pull them back together and continue to shrink it more. You can see that the area approaches 0 because even though the width approaches 8, the height actually approaches 0, and 8 times 0, along with anything times 0, is equal to 0. If we put our labels back and close it back up, you can see that this means the original area of the boundary was 0. Therefore, the open rectangle isn't actually any smaller than the closed rectangle, because the open rectangle is only different by the boundary, whose area is 0. What we're seeing here is a fundamental tension between 2 ways of thinking. In one paradigm, we have topology, who says that we measure everything in terms of sets, and that if a set includes even 1 point more than another, then it must be larger. On the other hand, we have measure theory, which says, yes, everything is measured in terms of sets, but even if a set contains infinitely many points, those infinitely many points may not take up any actual space, and therefore their measure can be 0. Our goal in the rest of this video is to remove the dividing line between topology and measure theory, or at the very least, make it a little bit thinner. In general, the formula that relates measure theory and topology is this right here. It says that if A is a subset of B, then the measure of A is less than or equal to the measure of B. We can take a look at an example of this. If we cut out part of a set, then we have created a subset, and the measure of that subset is less than or equal to the measure of the original. In fact, in this case, we can remove this less than or equal to sign and just make it a less than sign, because the measure of the subset is less than the measure of the original. However, that's not always the case. If we change this to a larger subset of the original, for example, just removing the boundary from the original, the measure is no longer less than that original one. The measure of this open set is actually equal to the measure of our closed set. This is the unfortunate reality that makes our original question so difficult and nuanced. The area measurement obeys this rule, but this rule isn't very strict. We call the area measure monotone. Monotone measures are nice because they say that if A is a subset of B, then the measure of A is not any bigger than the measure of B. But we want something even better. We want a new measure where if A is a proper subset of B, meaning B is strictly bigger than A, topologically speaking, then the measure of A is strictly less than the measure of B. In other words, there can't be 2 sets that are the same size, where one is a subset of the other. The whole must always be greater than the part. We call such a measure strictly monotone, or sometimes perfectly monotone. It's not immediately clear that such a measure is even possible. In fact, it seems impossible at first. However, the rest of the video is going to be showing you how I came up with a solution to this problem and created a strictly monotone measure on definable sets. I hope you stick around to the end of the video to see the solution, because the solution isn't that difficult to understand, but it is difficult to figure out, and it took me a few years to get the details right. Instead of looking at 2D sets, let's consider a finite number of points. As we increase the number of points on the screen, of course adding a single point increases the count by 1. Of course, every single point counts for exactly 1, no matter how many we add. We can also remove points, and every point we remove subtracts 1 from the count. Therefore, this so-called counting measure is a strictly monotone measure. The issue comes when we try to add a large collection of points to our set, like with this line. Since it consists of infinitely many points, our count suddenly jumps to infinity. But let's look at things a different way. Before we start, I want to point out that I'm going to show you a first attempt at a solution. This isn't an actual solution, and you'll see why it's broken in a moment, but the intuition will help us move towards the actual solution. In fact, this was actually one of the first things I tried when I first started this journey. We'll extend the counting function by making a new function called mu. I'll highlight it in red since this isn't the actual mu, only a first attempt. Mu is going to count the length of the lines as we add them in, and attach to them a term proportional to that length. We'll add this term omega here, which represents the length of a unit line. As I continue to add in more lines, you can see that this omega term continues to increase in value, proportional again to the length of the line that we are adding. We can also add area terms proportional to the term omega squared. You can think of omega as an infinitely large number, or as simply a term in a polynomial, but it's important that you recognize that omega is larger than any constant term, and omega squared is larger than any omega term. As we add and subtract areas, we're simply adding and subtracting from the omega and omega squared terms, depending on whether we're adding an area in a two-dimensional set or a length in a one-dimensional set. Look closely as the set is being built, both at its construction and how the terms on the left-hand side are affected by it. Notice that this boundary line isn't necessary anymore. It's just a contiguous part of the interior of the shape, so it doesn't need to be highlighted. In fact, let's just build this back up a bit more efficiently. We can also make this exact same shape by just adding a single quadrilateral instead of two triangles. But wait, the observant among you have already noticed a problem here. Pause if you want to figure out what it is for yourself. Even though we just built up the same set, the linear term in this polynomial is different than it was before. It used to be 15.2, but now it's 10.72. They're different because this time we never added a term for that interior line. But it wouldn't make sense that we need to add it. After all, we could just as easily have added a term for the other diagonal. Building with the upper and lower triangles, we'd end up with yet a different value for mu. This is one of a few reasons our current mu function is broken. It's not at all clear how we should divvy up the shapes in order to build them, and our mu actually depends on the way we build the shapes. This is a pretty awful property for a measure to have. The size of a shape should not depend on the way you choose to measure it. Again, it might seem like this is a lost cause, but it turns out there is a way to save this. We just have to find a way to assign values that's independent of how you choose to build the shape. Deciding what that function should be isn't that easy, but that's what I'll show you in the next section. Let's consider a line segment. We want this to have a size proportional to its length. But what kind of segment are we talking about? This could be an open segment, a closed segment, or even one that's half closed and half open, also sometimes endearingly called a clopen set. Interestingly, while the clopen interval seems unbalanced, it has a unique property different from the others. Notice that when we cut it in half, we end up with two more clopen intervals, and there's no overlap between the two. In other words, they tessellate perfectly. Two clopen intervals come together to make another clopen interval. If you try doing that with two open intervals, you have to fill this gap in the middle. And if you try it with two closed intervals, the middle gets double counted. Let's animate what this looks like. As we take more and more clopen intervals, half open, half closed, and tessellate them together, you can see that they perfectly meld together. Every time I add one single omega, I simply get a larger version of that same interval. They tessellate together perfectly with no overlap. Using this, we can measure all three of the different kinds of intervals. For a closed interval, it's going to have size omega plus 1 because we are adding a single point to the length of omega. Omega will be itself, of course, the half open, half closed interval which tessellates perfectly. We will have no constant term. Finally, an open interval will have size omega minus 1 because we've taken a half open, half closed interval and subtracted 1 point from it. Let's keep these over here for reference. We'll need them later. In the same vein, let's consider three different two-dimensional squares. One which is closed, one which is open, and one which is half open and half closed. We can consider each of these as a product of the reference terms on the left. The closed set is omega plus 1 squared. We can of course expand this out to get omega squared plus 2 omega plus 1. Similarly, we can expand the open one. It is omega minus 1 squared. Expand that into omega squared minus 2 omega plus 1. And finally, since the center one is the product of two clopen intervals, its size will just be omega squared. To check to see if this really works, we should be looking to see each of the details. Take a look at the difference between the left and the right hand sets. Notice that the difference between them is 2 omega minus negative 2 omega, which gives us 4 omega. This is precisely what we would expect. If you remove the boundary from our left-hand set, you'll notice that if you expand it, its perimeter is exactly 4 omega. The difference between the left and the right-hand sides is exactly 4 omega, which is the length of that boundary. This is our first hint that we're on the right track. Let's break this open square up even further and see if we can calculate the size of its individual parts. The two triangles on the left are congruent to one another, so they should have the same size as each other. Since the figure on the right is just a straight line, its size is only proportional to its length. Since it has no area, its omega squared term will be 0. Since its length is the square root of 2, the linear term will be square root of 2 times omega. And last but not least, since we have an open interval here, we're going to need to subtract 1 point from that. So its total size will be 0 omega squared plus root 2 omega minus 1. But this is now enough information to get us everything we need. Because the constant terms of the two left-hand triangles must be the same, and they need to total us up to positive 1 in the end, they need to both be plus 1, because negative 1 plus 1 plus 1 is positive 1, which matches up with our total. Similarly, since the two triangles are congruent, their missing linear terms must be the same as well. Because all three need to add up to negative 2 omega, a little quick algebra shows us that this must be the value. Taking a bit of inventory, these are the size values we got for the various shapes. For the triangle, we got its area, 1/2 times omega squared, minus half of root 2 plus 2 times omega plus 1. For the square, we got omega squared minus 2 omega plus 1. And for the open circle, well, we know that its area must be pi omega squared, but we're not necessarily sure what the rest of it is going to look like. But if we take a moment to analyze some patterns, we can make a pretty good guess. Notice that the perimeter of the triangle is the square root of 2 plus 2. In the expression for the size of the triangle, we subtract half of that term. Similarly, for the square, we subtract half of its perimeter. Both of them have constant term plus 1. So a reasonable guess might be that in general, we subtract half of its perimeter times omega, and then add 1, giving us this result for the circle. It turns out this is the correct guess. Let's see why. Let's take any shape, consider the circle for example, and cut it in half. Notice that two new open boundaries get created, both equal in size. We also create a seam of length equal to those two missing pieces. Since the two missing pieces need to exactly cancel out the seam, each one has to contribute minus omega over 2 times its length. The omega comes from the expression for length. We divide by 2 because two open boundaries get created and they share the open perimeter equally between them. Finally, it has to be negative because it must cancel out the seam that we've created in the center, and by splitting this in half, we haven't created or destroyed anything, so they must cancel each other out. Let's also hypothesize that, consistent with our examples, these are always plus 1 in the constant term. This is all a bit of mathematical trickery. None of this is formal, but it does come together to create a paradigm that actually does work. With that in mind, let's close up the circle and see if we can create a formula for its polynomial size by cutting it into pieces. I'll let the animation do the talking for a moment. Let's combine like terms, and we're done. I'll replace C for circumference with P for perimeter, because nothing we did was specific to a circle. And that means this formula works for any closed 2D shape, no matter how wonky. If we remove the perimeter, you just need to subtract P from the original formula, which means that you end up with minus instead of plus P over 2. This works for any open set. Using as a reference our intervals from before, we can say that the measure of a clopen interval is just its length times omega. And last but not least, if you have a finite number of points, you just count the number of points and add that to your total. In 2 dimensions, these 4 formulas are everything you need to make a strictly monotone measure, and it's not hard to prove that they are independent of the way the set is constructed. So, mu is a strictly monotone measure, which means it assigns every set a non-zero value, and it is independent of how that set is constructed. Let's see an example of that now. Here's a 2-dimensional set with some parts of the boundary included and some parts not. It's made of a 3x6 rectangle and a semicircle with radius 3. Here's one way to compute the size of it. If we measure the included boundary pieces, the semicircle has arc length 3 pi, and it's half open, so its size is exactly 3 pi omega, which we round to 9.42 omega. Because the straight line on the left is closed and has length 6, its total size is 6 omega plus 1. Using the formula here, it's easy to verify that this is the expression for the size of the interior. Now combine them together piece by piece, adding the polynomials, and you get the value for its size. Take a note of it in your head, because we're now going to do it another way. Let's make the closed version of it by adding in these red intervals. Using the formula for a closed shape, we get this value for the size. And now we can subtract off the 2 red parts, which have the values listed here. And when you subtract the polynomials, you get the exact same answer as last time. I just showed 2 examples of how to break it up, but you can prove that this polynomial size truly is independent of how you break it up. You could do it this way, or this way, or this way, or any other way. In fact, the best way to get a feel for it is to try it yourself. You could use this shape or any other 2-dimensional shape you want as an example, and as long as you use the formulas on the screen, the value you will get will be independent of how you construct the shape. If you do try it yourself, I encourage you to be patient and thorough and meticulous, because it can be frustratingly tedious at times to keep track of every piece. Despite having covered a lot in this video, there's a lot more questions that can be answered here. Here's just a few of them. Can this be done in n dimensions? The answer to this question is yes, and I'll explain it a bit more in a moment. Is mu unique? That is, are there any measures that satisfy the properties we want besides mu itself? And with reasonable assumptions, the answer to this is also yes. Mu is the only one. Is mu generalizable to any set? The answer to this is yes, but with some caveats. It requires a high level of abstraction called non-standard analysis to work, and it's not at all clear how to actually calculate the values, even though you can prove such a measure does exist. One might suspect that next steps would be to generalize it into fractal dimensions, that is, omega to some fractional power, but I have not done that yet. Do the polynomials themselves, that is, their zeros, their derivatives, etc., have any significance? The answer again is yes, with some caveats. I don't know of any uses for the zeros or the derivative, but I can show you some very cool properties the polynomials do satisfy, and in a moment I will. Finally, are there practical applications? The answer to this is maybe. While I've worked for a long time to develop the function mu and figure out some of its properties, I haven't been able to come up with any specific theorems that give this practical use. However, I have managed to solve some practical problems, such as finding the area of fields that are cut by roads using this method. Let me know in the comments if you'd be interested in seeing that. In more detail on question 1, can this be done in n dimensions, I'll refer you to any source on the intrinsic volumes. These functions also go by other names, such as Quermass integral, but the intrinsic volume normalization from geometric measure theory described mu quite perfectly. The total size function mu is just the term-by-term polynomial sum of the intrinsic volumes times omega to their dimension, like this. Again, let me know in the comments if you'd like to see more of this in detail, but I can also refer you to my preprint archive paper linked in the description. Lastly, I'll point out a couple properties that the polynomials themselves have, which are really convenient. The first is that mu respects polynomial products. that is, the measure of mu of the Cartesian product of a and b, is just the product of mu of a and mu of b. The second property is that mu is homogeneous, which means that if mu of a is some polynomial function, then if you scale a up or down by a factor of alpha, its new size will simply be that same polynomial evaluated at alpha times omega. This captures the idea that volume, surface area, perimeter, and other measurements scale homogeneously with their dimensions. Thank you so much for watching, it really means a lot. Again, let me know in the comments if there's anything you'd like to see answered in more detail. I'll try to answer every comment. If you enjoyed the video, please leave a like and a comment. It really helps the video gain traction with the algorithm gods. As I mentioned, a link to the paper this is based on is in the description, but be warned, it is a preprint, which means it has not been peer-reviewed, and I certainly made mistakes in it, especially in the non-standard analysis section. As I said, thank you for watching. This video took a lot of time and effort to make. If you'd like to see more content like this, consider supporting me. Details are in the description. Ciao for now.